Hello guys, nice to see you. How was your weekend? Hope everything was fine. Okay, so last Friday we finished our discussion with a statement that it's necessary to read something in the textbook about electric field lines. So I believe we will start today with a very brief introduction just to refresh in your memory what is electric field line and why we use this concept. And afterwards we will shortly shortly after the discussion very briefly the concept of electric field lines, we will move forward to the flow of electric field and one of the most important concepts in electrostatics, Gauss Law, which defines the relationship between the flow of electric field and electric charge enclosed by a closed surface. So flow through the closed surface of electric field and magnitude of electric charge, which is enclosed by this surface. So that will help us to, under certain conditions, very easily solve problems for determining electric field of different distributed, like continuous electric charges and continuum of electric charges. And as we discussed before, this is one of the main tasks of electrostatics. If we have a set of some system of electric charges, we want to know electric field in the space around these electric charges in any point. So that's since Gauss law helps us quite in a simple way and very efficiently solve this question, specifically for distributed charges. That is very useful and important concept. So, okay, let us switch to the other camera. You can see this whiteboard. And as a short reminder, so the concept of electric field lines is used to represent graphically electric field, and actually not only electric field, but also any vector fields. Since electric field is a vector field, any vector fields can be very efficiently represented and clearly by field lines. So in our particular case, this is electric field lines, and their definition is that electric field vector is tangent to the effective field lines at every point. So this is the main condition which defines how we draw electric field lines. So at every point of this electric field line, electric field vector is always tangent to this line. And the line has direction. It's specified by an arrow. And the direction of electric field line is defined by the direction of force which acts on a positive charge, like test charge, which is located in this electric field. So that's why, let's say if we have some positive charge, we know that if we put some small test positive charge Q naught, and this is plus Q, that along this line which goes through the two charges, there will be some electric force exerted on test charge, and it will be oriented away from the source electric charge. Because charges with the same sign, they repel from each other, and this direction will also define the direction of electric field lines. So that's why we can draw, if we get rid now of this. We can draw that electric field lines kind of originate on positive electric charges and go radially in all directions. If we have negative electric charge, then these electric field lines, they will be kind of directed toward the negative charge, and it will look like this. So we can make a statement based on this, that electric field lines, they kind of originate at positive charges and spread from them, and terminate, finish themselves on negative electric charges. And this concept is very useful not only to specify the orientation like of electric field in space, but also the strength of electric field, because the concentration, the number of electric field lines which goes through a surface perpendicular to electric field lines defines how strong electric field is in this area. So by changing the density of electric field lines, we can easily graphically represent direction and strength of electric field. Okay, so this is the main concepts you need to know about electric field lines, and now we can proceed further and go for define what is electric flux. So electric flux E is equal to the product of electric field and the area. If we have this area segment oriented perpendicularly to the electric field vector. So let's say we have some surface element, and perpendicularly there are electric field vectors which go through this area. So this is the definition of electric flux, and in international unit system, units for this electric field flux will be Newton per Coulomb, which is units in SI for electric field, and times square meter, like area. So if we have some angle between the normal to the surface and electric field vector, then this arrangement of the surface element with respect to the electric field vector should be taken into account. That's why if we have, let's say, some surface with normal vector to the surface like this, and electric field vector in this direction, there will be some angle alpha between them. And in this case, electric field flux is equal to the product of electric field strength area times cosinus alpha. So from this equation, we can already see that the maximum flux of electric field will be through the surface which is perpendicular to electric field vector. If it's oriented at some, if it's like normal to the surface is oriented at the angle of 90 degrees, or this is in radians pi divided by 2, then there is no flux through this surface, because in this case cosine 90 degrees will be 0, and flux of electric field will be also 0. We also need to take into account that flux can be positive or negative. So in this particular case, when the alpha is smaller than pi divided by 2, the flux is positive, because cosine alpha will be positive. And if alpha is larger than pi divided by 2, then flux will be negative. So these are general statements about the concept of flux of electric field. However, so far we considered that electric field is uniform, but it's not the case in general, and that's why we need to take into account this option when the electric field will be not uniform across this area where we want to determine the flux of electric field. So in this case, obviously we need to consider some small element of surface within which we can assume with certain accuracy that electric field is constant. And such small area element can be represented by delta A vector, which is delta A, it's this small area, which we consider within which the electric field is constant or doesn't change much, times unit normal vector. So this is unity vector, which only defines the direction of the normal to the surface element with the area delta A. So it's convenient to operate with such vector, which defines small element of area, because it defines simultaneously both area and its orientation. And now we can write that according to the previous equation, which we had for the flux, we can write that I component of flux of electric field, which goes through this particular small element of the surface, will be equal to the electric field next to this element of surface, which is considered constant because the surface element is very small, times delta AI times cosinus alpha I, which defines cosinus alpha, like alpha I defines the orientation of this particular element with respect to electric field in this area. So that is nothing else as the dot product or scalar product of two vectors. We have vector electric field vector times delta A delta A vector. So this we keep in mind, and also of course we want to calculate full flux, so we can actually put here also delta pi because it's only a small flux through the small element of the surface, but we want to calculate electric field flux through all surface, so we need to sum up these fluxes through small elements which form whole surface. In this case, the total flux will be equal to the sum over all elements which we divide surface, scalar product of electric field vector times delta A I vector. Actually, here we also need to put I. So if we divide this surface in elements which are extremely small, that delta AI approaches to 0, then of course we can in general case represent electric flux where the integral over the surface which we are interested. So it will be integrals. Here we can write surface of the product, scalar product, electric field times dA. So this is the general equation which allows to calculate electric field flow of flux through any surface which is in the case of non-uniform electric field. So now let us specify which specific surface we are interested in. In our case, we are interested in so-called closed surface. Means that closed surface, it's a surface which divides space in inside and outside parts. And in order to move from one part to another, you always need to go through this surface. So if we have some sphere, then the surface of this sphere is a closed surface which divides space into inside space, which is enclosed by this surface, and outside space, which is outside from this closed surface. So this is definition of closed surface, and we need to calculate and understand how we calculate electric field flux through closed surfaces. So let me share this screen. Okay. Now you see here an example of closed surface, and which is located in some electric field. So depends on the side of the closed surface. If we divide this closed surface to many elements, like small elements, depends from which side these elements are located, we can experience different cases. So for instance, let's go from the left one. We see that the orientation, this vector delta A3, it's the same orientation as the normal to this small surface element, forms a large angle larger than pi divided by 2 with the electric field vector. In this case, as I mentioned before, we have negative flux. And then we have another example when these vectors are oriented at right angle to each other. That's why in this case we have zero flux, because cosine of 90 degrees or pi divided by 2 will be equal to 0. That's why we don't have any flux through this surface element. And on the other side, small element, we have small angle between the electric field vector and the normal to the surface element. That's why our flux is positive. So in other words, we have some electric field lines which go inside the closed surface and some which go outside. And what we are interested in when we calculate the flux of electric field, we are interested in some so-called net flux of electric field. It's the difference between number of electric field lines which go inside the closed surface and go outside. In this particular case, if we have more electric field lines which go inside the closed surface than those which are going outside, we have negative electric field flux. If it is in the contrary, we have positive electric field flux. So this keep in mind, because we need to deal simultaneously with orientation of electric field and normal to the surface of surface element with respect to which we want to calculate this electric field flux. Okay, let us come back to the whiteboard. And in this case, when we have closed surface, we need to a bit change this equation for electric field flux. In particular, electric field flux in the case of closed surface, we mark this integral with such circle, which means that we integrate over a closed surface, not just surface. And here we write that we integrate the dot product of electric field vector and this element, small element area vector, and this can be represented without vectors as integral over the closed surface En times dA, where En stands for the component of electric field vector in the like projected on the direction of the normal to the this small surface element dA. That is the way how these calculations should be done in definition of electric field flux through a closed surface. Now, when we define all key moments and know what is electric field flux, how to calculate it specifically for the closed surface case, we can proceed further and actually work on the Gauss law. So for this, As I mentioned before, Gauss law defines the relationship between electric field flux through the closed surface with the electric field, with the electric charge, which is enclosed in this surface. So this relation is very important and can be very useful in terms of calculating electric fields of some continuum of electric charges. That we will do a little bit later. So now let us consider some positive charge and some sphere, which we consider as our closed surface around this positive electric charge, and this sphere will have some radius r. So if we choose some surface element on this sphere, we know that electric field vector has radial symmetry. It spreads as straight lines in all directions from the electric charge, which is in the center of this sphere. And that's why we can write that. So here is the normal vector to this surface element. And here is the electric field vector. So in this case, they are aligned parallel, and we can write that the flux of electric field through this element dAi can be calculated as follows. We have vector product of electric field and vector dAi. And since these vectors are parallel, we can skip this cosine alpha, because cosine alpha for parallel vectors will be unity, and we will have just product of absolute values electric field times dA. So now we want definitely to calculate total electric field flux through all surface of this sphere. And in this case, total electric field flux will be integral over the closed surface of this sphere times electric field vectors times dA vector. This is equal to just product of absolute values, because they are parallel at every point. What is important, they are parallel in every point of this sphere. This sphere, of course, not very nice, but we imagine that it's ideal sphere. But in this case, when this sphere is ideal and this charge is located in the center of sphere, because of the symmetry of electric field created by the point charge, at every point of this sphere surface, electric field vector and normal to the surface will be parallel. So that's why we can write such product of absolute values in the integral. And again, taking into account spherical symmetry of electric field originated from point charge. Since it's located in the center of the sphere, electric field will be constant at each point of this sphere, because it will be at the same distance r from the source of electric field. And that's why we can take out from the integral a constant value, which is electric field. And we have integral over the closed surface, dA. And this integral over closed surface will be just area of the surface, of the sphere, which we consider. And we know that area of the sphere, so we can write that integral dA is equal to A, and this is equal to 4 pi r squared. And we also know what will be the strength of electric field at this sphere surface, because we know Coulomb equation. So electric field will be equal to Coulomb constant times Q, which is electric charge of this point charge, which we consider, and divided by r squared. So now we need to multiply electric field, which is this equation, by the area of the sphere, and we will do it on the next slide. In this case, total electric field flux will be equal to the KE Q divided by r squared, then times 4 pi r squared. R squared and r squared we cancel out. Then we have 4 pi Ke Q. Now we take into account that the Coulomb constant is equal to 1 divided by 4 pi epsilon 0. Do you remember, guys, what is epsilon 0? What parameter is this? Yeah, permittivity of free space, of vacuum. So it's a constant value, and you need to remember this for sure. Good. Let's then continue. If we substitute this value in our equation, we can write here that the total flux through this surface will be equal to Q divided by epsilon 0. Good. So this is our, at this point, final expression. And we see that the total flux of electric field through the closed spherical surface around a point charge is defined only by the electric charge and some constant, which is permittivity of free space. But it doesn't depend on the radius of the sphere. So we can take larger or smaller sphere, it doesn't matter. We have this constant electric flux, which is defined only by the electric charge, which is enclosed by this sphere. So now let's go for a bit more general case. Let's say we have positive charge. We have some sphere with this positive point charge in the center of this sphere. And then we have some surface, closed surface with random shape around them. So now we know that there are some electric field lines originated on this electric charge and going in all directions. We mentioned earlier that the electric field flux, the net electric field flux through the closed surface is defined by the number of electric field lines which go through this closed surface. So we know already, we have shown this, that let's call it area 1, and this will be area 2. We already have shown that the flux, electric field flux of an electric charge, point electric charge Q in the center through this spherical surface around it will be Q divided by epsilon 0. And we see that all lines of electric field, they go through this sphere. That also true for this random shape closed surface. The same amount of electric field lines are passing through it. And that's why electric field flux through surface 1 is equal to Q divided by epsilon 0. And this is also true for the surface A2, which is random shape. It's also equal to Q divided by epsilon 0. So this concept can be quantitatively, so this is graphically shown. We see that the same amount of electric field lines pass through both. If you're interested more in the quantitative derivation of this provement of this statement, it's a very useful concept of solid angle, which is full solid angle for all surface in the space is equal to 4 pi steradian. So if we consider electric field flux in terms of not through some specific area, but through the solid angle, then for both surfaces closed, for all kind of closed surfaces, they can be described with a full solid angle, which is 4 pi steradians. And that's why it doesn't matter if it's ideal sphere or it's some random closed surface with like random shape. It will also be full solid angle in 4 pi steradians. That's why the flux of electric field of a charge which is located enclosed by this closed surface will be always the same. It will be Q divided by epsilon 0. So now we need to consider another case, because so far we considered only charges which are inside this closed surfaces. But what will be if we have some charge Q, let's say positive charge, outside a closed surface? So in this case, we also can draw these electric field lines, and some of them will go into this closed surface and then will go out. Go into and at some point go out. So it is obvious that if we have electric charge outside the closed surface, the number of those electric field lines which enter the closed surface will be equal to the number of those electric field lines which go out from this surface. And since we are interested in the net electric field flux, the net electric field flux will be defined by the difference between the number of electric field lines which go inside and those which go outside. If they are equal, we will get the case when electric field flux of electrical charges, which is created by electric field, which is created by charges located outside the closed surface, will be equal to 0, because we have the same number of entering and exiting electric field lines. So now we keep this in mind, and so that means that in order to have some electric field flux through a closed surface, electric charge which creates this electric field should be specifically located only inside this closed surface. So now let's go to another slide, and we need to consider a case. What if we have not just one electric charge? Let's say we have some closed electric, closed surface, and we have a bunch of different electric charges. They can be positive, can be negative, all type of possible combinations. So in this case, in order to calculate the electric field flux, we need also to integrate this vector, this scalar or dot product of two vectors, electric field times dA, when we select certain small area on the surface of this closed surface. And in this case, we need to highlight that this is not just electric field vector which is created by one electric field, but it's because of superposition principle, we need to calculate a vector sum of all electric field vectors created by all charges in this given point where dA is located. So this will be the, let's call it, effective electric field created in this particular point, created by all charges enclosed by this closed surface. And that's why we can write that it will be integral over surface. And here it will be like E electric field vector created by first charge, second charge, then nth charge times 2 dA vector. So this is the way how electric field vector of a system of electric charges should be calculated. Another example we need to consider to make it clear is the following one. Let's say we have some set of closed surfaces, like 3 closed surfaces. Will be surface 1, surface 2, and surface 3. And in surface 1, we have some positive charge, Q1. In surface 2, we have 2 charges, one positive, Q2, one negative, Q3. And in surface S3, we don't have any charges, but we have one charge, some positive charge, plus Q4 outside. So what we can tell about this? Electric field flux through surface 1 will be equal to Q1 divided by epsilon 0. Electric field flux through surface 2 will be equal to Q1 plus Q2 divided by epsilon 0. Here we need to specify if, because we have positive and negative. So if Q2 is, like by absolute value, is equal to Q3, then they will cancel each out. And in this case, net electric charge will be equal to 0. And if net electric charge enclosed by a closed surface is equal to 0, then this flux of this electric field will be also 0. If they are not by absolute value equal to each other, then we will have some net electric charge, and that will define what electric field flux we will have. Then also electric field flux through the surface S3 is equal to 0. Obviously, because we don't have any charges enclosed by this surface. And as we have shown before, if we have electric charge which is located outside closed surface, it doesn't create any electric field flux. So charge Q4 will not create any electric field flux. And that's why, summarizing all these statements, we can write that electric field flux is equal to integral over surface of a dot product electric field vector dA vector, and this is equal always to Q in divided by epsilon 0, where Q in is the charge which is located inside this closed surface, enclosed by the surface. So this is the well-known and very useful Gauss law, and it can be used to solve for unknown electric field vector in any point outside the in the space around electric charges, either isolated or continuum of electric charges. But practically, it's very convenient to use this law in those cases when we have some symmetric features of electric field. So there are certain conditions for choosing the correct surface, like closed surface, around these symmetric electric fields in order to make the solution of the problem as simple as possible and as convenient as possible. So first would be that the value of the electric field should be constant over the portion of the surface. Like over the part of the surface, it should be constant. Another condition that electric field and dA vector, electric field vector and dA vector should be parallel or perpendicular to each other, also for a portion of this closed surface. And one more, that electric field vector or electric field is equal to 0 over also a portion of the closed surface. So different portions of the closed surfaces, they are also called Gaussian surfaces, can satisfy different conditions of these three which I mentioned, but at least each of them should satisfy one of these conditions in order to apply this Gaussian law very efficiently and solve problems for finding electric field vector in any point very straightforward and simple. So we will do these examples next lecture, and you will see that for some cases, it is really a simple solution to calculate electric fields of continuum electric charges, which in other way would require a lot more calculations and more complicated integration. Okay, so I think today we are done. So any questions, guys? Tell me. If you have any questions along the lecture, please don't hesitate to interrupt me and ask your questions so we can discuss this on the way. It would be very good working environment if we have more communication. But let's say if now we don't have any questions, I thank you for attention and hope to see all you on our next online lecture, which is on Wednesday. Okay, have a good evening and take care. Bye-bye.